MDM4U 6.6, Applying Matrices to Probability Problems. So what we're going to be learning about is a Markov chain. And this is a probability model where the outcome of any trial is dependent on the outcome of the previous trial. So this is dependent probability. Using matrix operations can simplify probability calculations, especially in determining long-term trends. So we're going to learn some definitions first, and then we'll see this applied to a problem. It'll help with the context after we know all of the definitions. So the initial probability vector. The initial state of a Markov chain is a row matrix where each entry represents the probability of a potential outcome. The sum of the entries in the row is equal to 1 because each of these different outcomes that are possible is represented by event A, event B, and event C. So this is what it is initially to start. Now, the characteristic of a Markov chain is that it has a predictable behavior based on previous results. So this transition matrix P, if you multiply it by this initial probability vector, you can simplify calculations involving conditional probability. So a transition matrix is a square matrix which represents the conditional probability of each outcome or state based on the previous trial. So that being said, this matrix is representing the probability of each state or each outcome. So this is a column for A, B, and C. That's the likelihood of that outcome happening, depending on what happened previously. So this is a conditional probability statement, the probability of A given that A has happened. So this row represents A has happened previously, B has happened previously, and C has happened previously for the third row, and so on. So what we're interested in looking at is if this process carries on, what is the long-term trend that is likely to occur? So if we look at the nth step probability vector, this is meaning that we will see the probability of each outcome or state as a long-term trend. So any step in the process, meaning how many times we've gone through that transition matrix, we have our initial probability vector times p to the power n. And if you've done matrix multiplication, you'll realize that matrix multiplication can be very time consuming. So this is S at n represents the probability of each state after n trials. And this is a way of showing that under this definition, just looking at each of the different terms consecutively, that we can express this formula as either the initial probability vector times p to the power n, and this is helpful when you have technology that you can calculate p to the power n very quickly to find an instance in a certain trial, for example, the state after a certain number of trials. Whereas this form is helpful when you're calculating by hand and you can substitute in the previous step and do them consecutively one after the other to figure out the values. So we'll get to this with our example shortly. The steady state vector, a probability vector that remains unchanged when multiplied by the transition matrix. This vector represents the long-term trend. So if Sn, the nth step, is the same as the nth step times p, meaning no changes happened, or that the nth step is the same as the next step, n plus 1, then it's reached a steady state. And a Markov chain will reach a steady state whenever it's a regular Markov chain, meaning that p or some power of p has no zero entries. A regular Markov chain will reach a steady state regardless of the initial probability vector. So let's look at a problem. Markov chains and tree diagrams. An employer determines that an employee has a 95% chance of being punctual the first day of work. If an employee is punctual the previous day, then there's a 90% chance of being punctual the next day. And if an employee is late the previous day, there's a 60% chance of being punctual the next day. So the component that makes this a Markov chain style question is that it's these conditional statements here. And what we have is determine the initial probability vector. So the initial probability vector gives the probability of each state initially. So being punctual is 95%, so 0.95, and late is 0.05. The transition matrix summarizes those conditional statements. If someone is punctual, we'll have this row representing punctuality. There's a 90% chance of being punctual the next day, so 0.9, and that implies that there's a 1% chance of being late because this adds to 1. Now, if someone was late the previous day, there's a 60% chance of being punctual the next day and a 40% chance of being punctual that following day. So, when we multiply these together, determine the value of S1. So we multiply the previous step times P, and that is equal to this number right here. And what this means is if we look at this number, 0.885, this is the probability of being punctual on the second day. Let's take a look at the ways that you can be punctual on the second day. Just looking at the final outcome on the second day, you would have 0.95 times 0.9 to get to this result, plus 0.05 times 0.6. And that's exactly the process that's happening with matrix multiplication of the initial probability vector times P to get this value. So it's a quick way to get a result without having to draw a tree diagram. And you can imagine tree diagrams with many outcomes becomes very problematic to try to draw in one space. It gets messy. So this is a very compact way of writing that material. So if we look at S2, or the second step, that means we've multiplied by the probability, the P matrix twice, the transition matrix. So we'll multiply the previous result, we're using the definition that's easier by hand, times the transition matrix one more time, and we get this value, which is on the third day, 1, 2, 3, 4 ways in order to get punctual on the third day. So it calculates all of those outcomes easily using matrix multiplication. Lastly, determine the steady state vector for this problem. We were told that if we have an nth step that is the same whenever you multiply it by the transition matrix, that means no change has occurred, then it's reached a steady state. So assume that PQ is our steady state, and P represents, in this case, punctual, Q, which typically means failure in probability, but in this case it will mean late. So if you were to multiply this through, this would be the resultant matrix. And then what we are given is two linear equations. If you set Q equal to this entry, that's your second equation. And what helps is knowing that P plus Q is equal to 1 is another constraint. And then you can solve this system of linear equations using analytic geometry. Okay, so that means that we isolate one of the variables in an equation and substitute it into another and solve. This is an easy substitution from equation 1 into the third equation, P plus Q is equal to 1. And then we get Q is equal to 1/7, and that implies that P is equal to 6/7. This is the long-term probability vector for this problem.